Okay. All right, guys. So I hope you guys are doing well. Okay, just make sure that you stay safe. I don't know about the COVID situation right now. It seems like the number is creeping back up again, and just want to make sure that you guys sort of like stay alert a little bit of things around you. Okay. All right. So what we have for you today is just to finish up this handout, and we're going to move on to another kind of waves, which is light, and that's what's going to be something that's no calculus involved material. So it's kind of good. Okay. So good thing about this module over here about waves is we are pretty much dealing with just well, I would say mostly algebra, even though you have some differentiation, but that's very minimal. And the rest of the whole thing is more like a geometry, just like, functions, dealing with all those stuff. Okay. So it's kind of good. Okay. Now, if you guys had a chance to play with the simulation, all right, if you sort of like remember what we did over there, so that's allow you to be able to evaluate or determine what wavelength of the sound that you sent into an air column will eventually generate something that is a standing wave. Okay, so there is another word when they talk about this standing wave, because we already said that other kinds of wavelength will just disappear. I mean, disappear mean it's not going to be dominant in relative to the one that actually fits the boundary condition, right? So sometimes you might hear the word of the resonance. It's sort of like come together in the sense that every time that you have a resonance, in if you remember in mechanics, then you just say that if you sort of like apply some forces, and then it turns out the rhythm of the force that you apply to the system matching the frequency of the system, just like what you saw in this simple harmonic motion, like mass on spring or in the simple pendulum, then you can make that oscillation grow even larger in amplitude. Okay, does that make sense? So you can imagine like when you sort of like swinging something, you on a swing, let's say, and then your friend just come and help you, and if your friend just kind of like push in the same rhythm as the swing that is oscillating back and forth, then you're going to get higher and higher and higher and higher. That's we call the resonance. It just means that everything just in sync, in the perfect timing and everything. So the way that you can sort of transfer the energy from the source to the system is going to be at best. That's a resonance effect. Okay, it's pretty much a quite same thing over here in the sense that um, when you send in the sound with different wavelengths, there will be like some particular wavelengths that sort of match the natural frequency of that tube or of that air column. So that's why you sometimes you can heard people talking about this one under the topics of resonance as well. And this air column sometimes are referred to as a resonance tube, because it's a tube that pretty much like, just picking up some wavelengths that's allowed to be oscillating efficiently in this tube. Does that make sense? Okay. So that's what I mean, they are pretty much like the same topics over here: the standing waves, the interference of sound, and resonance in air columns. They are pretty much talking about the same underlying principle over here. Okay. All right, guys. So let's dive into it, shall we? How can we actually calculate this one? Okay. So you guys, any question on this one? I think you guys tried that simulation already, yeah? Okay. So I think maybe the best way to get things started, and now we're going to get more quantitative here. So what we are going to do is I'm just going to open up that uh, website again. That sounds good. All right. So let's try that one. Okay, here we go. All right. And now we are going to look at the numbers now. Look at the numbers. Okay. Let's it reload a little bit. Okay, here we go. Oh, it's disappear again. All right. Okay. All right. Now look at this. So let's say if I pick, in this case, just start with the open at both ends tube. Okay. So I'm going to pick this one. So now both ends are open. And now let me pick like some like easy number. Let me try like a 2 meter. Would that allow? Okay, that's kind of short. Let's go 4. There you go. All right, now, so from our understanding, if you look back at our slide and you kind of like, okay, Dan, I remember what we did last time was like, if you would like to fit this one into this both ends open tube, then you have to pick the wavelength to be lambda equal to twice the length of the tube. Does that make sense? Okay, so yeah, because we want to go from antinode to antinode, right? So you have to go through, at least the easiest one is go passing through one node in the middle, and that allow you to determine that the wavelength is twice the length of the tube. So let's try that one here. Here you go. So if you assume that the wavelength is supposed to be twice the length of the tube, hey, oh, that's just perfect. It's an 8-meter wavelength that I can put in. And let's run this one and see how it goes. See? So I'm just showing you the resultant wave first. Okay. So this is the oscillation that happens after what? After you have sent in the original, and the original eventually get reflected. And then you can imagine that one wavelength is traveling. You can look at maybe the blue. The blue is going to your right side and the orange one going to your left. And then when you have two waves meeting at one point and then they move in opposite direction, they have interference, and that interference generate the bottom figure. Does that make sense? Okay. All right. And now in reality, as I said, all right, you have like multiple wavelengths going on, multiple reflection, even though I think I kind of know that in this simulation, when you put extra, sort of like a multiple wavelength to it, it seems like it's taking into account the amplitude or something that when you reflect out of open end tube, it's kind of like hard for you to see. So that's why I think they get rid of those, I guess. All right, that's my guess. All right, so let me show their summation over here. See that? So this is a nice simulation there. So the green curve in the upper tube there, that's showing you the summation of the blue and the orange at all time. And that green is being copied down at the bottom. Cool. All right, and this works. Now, let me try, if I send in some wavelength that doesn't match twice the length of the tube. So that's mean, so if I send in the wavelength that's other than 8 meter, so now let me change to something weird, like let me put in 7. So now it seems like it's not going to work perfectly, even though it's still not bad. But as you can see, the summation doesn't seem to go really well at the bottom now. And now it's harder for you to see that now the green and the one at the bottom look a little bit different, if you notice. See? The green up there, it looks like, Ajahn, it still look okay. Even though it shifted a little bit, right? If you look at the green. But then if you look at the bottom one, the green on the top and the resultant wave at the bottom now doesn't seem to synchronize anymore. And the reason for that is because now when you have the condition that things does not match, then you can see better the multiple reflection, because the reflections now come in at like different phase now. So they are pretty much get separated. So you will be able to see those multiple reflection much better. And you can add some more, and I think the simulation will go a little bit slower, but that's what it is. Okay, so things go crazy in there, blah, 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 blah. And that's why if you look at just the green one, it just only take into account just the first and maybe the first reflection, and then you're done. All right. In reality, you have to you have to add infinitely many reflections actually to get to the bottom. All right. But anyway, just forget about the details at this point. I think the key point to take here is, okay, I can just speed up this one a little bit. So now I think you understand what it is trying to do. So if I just change the wavelength to some other thing, now let me try like about maybe some crazy number 5 something, and then I run. Now this is really bad. See that? The one in the bottom doesn't really give you the combined wave, has like super slow, super small amplitude now. So that's why the contribution of the sound at this particular wavelength will be not much in comparison to the one that fits perfectly. All right, now keep going. So let me try, go down again. And then let me try put like 4 if possible. All right, I'm gonna put exactly 4 there. Can you guess what will happen here? Now you fit one exact wavelength into this tube. And from our our calculation or our slide right there, that's our second condition. If you pick the wavelength to be exactly the length of the tube, it seems to work. So let's try that. Run. See, that's very nice. So now the curve in the bottom give you the maximum amplitude possible one more time. So this is another standing waves in the air column here. And now you can play around with it. And now you can move on to some other wavelength. I can pick like maybe what, like 1.5, somewhere there. And then you can play around with this. There you go. It's almost there. There you go. Somewhere around here. We're close enough. And then now you can see that you get the very good resultant wave one more time, on and on and on. Okay, so this is how you can play around with this. And that conclude the simulation over here. Any questions? I think so far so good. All right, so I hope you understand the figure over here better. Now, hopefully that you understand that the actual wave will not split into a loop. I mean, especially like in a string, like it's impossible for a string to just split into a loop, but it's just a quick movement that sort of like give you a perception of a loop. Okay, but in sound, forget about it. All right, it's not going to be a loop for you per se. Okay, all right, now let's do the notation or terminology a little bit, guys. So now because we know how to determine the wavelengths that generate standing waves in air columns now. So look at the fundamental one. When I say fundamental, mean that is the first possible frequency that allowed in this tube. Okay, and because now you know the condition of this one is the wavelength has to be twice as long as the length of the tube. So the frequency is V over 2L, correct? Okay, so far so good. So what we have here means this is called fundamental frequency. Fundamental frequency. There you go. All right. Now, if you move to the next one, you can see that this one, I can rewrite this one as 2 of V over 2L. And the V over 2L is just fundamental frequency here, right? So that means the next available wavelength or frequency is going to be twice the frequency of the fundamental frequency. You guys with me? Okay, so these numbers right here, number 2, is going to give you the name of this mode of oscillation. It's a second. And because it's twice the frequency of the fundamental frequency, we call it the second harmonic. Cool? I don't know is that cool or not, but that's what it is. Okay. And you can say that the fundamental frequency is your first harmonic. That's what it is. And now, and can you move on to the next available frequency? You can see that, oh, at the next one, the wavelength had to be 2L over 3. So the frequency is going to be 3 times V over 2L. And once again, V over 2L, you already identified it as a fundamental frequency. So that means the next available frequency is going to be 3 times. So we're going to call this the third harmonic. Cool? All right. And because starting from the fundamental, that is your first frequency that's available to you to generate standing wave. The next one is second harmonic. However, is the next one from the bottom, which is the next one from the fundamental. Sometimes people refer to this one as the first overtone. So it's the overtone, it's the next tone over from the fundamental. So this is the first overtone. And then you can keep going with the second one. So in conclusion, for the both ends open tube, the first overtone will be second harmonic. Second overtone will be third harmonic, on and on and on. Cool? All right, now try again. This will clarify the terminology used here if you compare this one with the standing wave in one open, one closed air column over here. So start from the fundamental, guys. So what we have over here is, in the case of fundamental, remember we start from the antinode, we end with the node. So you can fit the wavelength that is 4 times the wavelength in there. Cool. Okay. And then what you can see over here is now you can write your frequency. So let me put on the side here. It's actually already written there, but let me put big one here. So the frequency available here, I can put 1 in there just to indicate that this is your fundamental. It's going to be V over lambda, and it's going to be V over 4L. So far, so good. Now move on to the next one. All right. Oh, okay. Let me put on here, this one first. It's fundamental. Okay. This is fundamental frequency. Okay, no problem. Now, the next one, you're going to call it the first overtone, right? That's what we agree. All right. That's first overtone. But what kind of frequency you're going to get in the first overtone? You come back here and take a look at it. And then you say, oh, Adan, by the condition, you start from anti-node, you end with the node with extra twist in the middle. We already found out last time that is 3/4 of a wavelength is the length of the tube. So that means the wavelength that fit this condition is going to be 4/3 of the L. So what I can say is the frequency that shows up here is going to be V over 4L over 3. I flip 3 up to the top. Okay. And now you recognize that the V over 4L is just the fundamental frequency, yeah? Okay. So that number 3, that's showing that now your first overtone is 3 times the frequency of the fundamental frequency. So that's why we're going to have the third harmonic here as your first overtone in one open, one closed ends tube. Cool.
Okay.
Okay, everyone kind of like quiet today, but I hope everything is good. All right, and then you can guess what should happen next. Okay, so next one, once again, you start from the anti-node. Oh, sorry. You start from anti-node, okay, and you're going to end with the node, but now you put 2 twists into it. So you have 2 nodes in between. So over here, you can say, okay, what you have here is my 4/5 of the lambda. I mean, 5/4 actually. It's going to be, okay, so it's going to be 5 over 4 lambda. It's going to be L. So the lambda is going to be 5. Oops, sorry. I think I got it mixed up over here. Yeah, there you go. 4L over 5. And then your frequency that fits this condition is going to be 5V over 4L. Cool? Alrighty. And then what you have here is now, once again, it's 5 times the fundamental frequency. So now you can call this one your 5th harmonic. Cool.
Okay.
And 5th harmonic here is going to be your 2nd overtone. Then that's it. It's done.
Okay.
Okay, so this is sort of like terminology that is going to be used in this topic over here. Plus, sometimes in the textbook, because we already sort of like portray this whole standing waves thing using like a loop type figure over here. So there is a very quick sort of like comparison or a quick calculation that you can do after you drawing a figure. So look over here. Every time you look at a loop, that's equivalent to half a wavelength all the time. Can you see that? That's half a wavelength here. I highlight like a thick red over there. So what you're saying over here is every time that you have a complete one wavelength like that, if you're going to draw it as a loop, it's going to look like this, right? So that means every time you considering one single loop, one loop here, it will always equivalent or equal to exact half the wavelength. This is wavelength over 2. So you can use this if you like. One loop is wavelength over 2. And then you just count the loop. For example, over here, the one in the middle. So you say, oh, Dan, this is 1.5 loop. So you might be able to say this is 1.5 loop, but each loop is lambda over 2. So you get 3 over 4 lambda equal to the length of the tube anyway. Same result, right? You can end up with the same results right there. Okay, so if you prefer, and I think many of you like this kind of loop counting thing, so you can do it. It's exactly the same. It's the same thing as you recognizing that what is going to be the wavelength of the wave. Okay, but you're doing it through counting the number of loops in your system. All right, guys, it's any questions so far? All right, so if not, let's take a look at the example right here. Okay, so you have a section of drainage covered to 1.23 meter in length, makes a howling noise when the wind blows across its opening. So this happens all the time. Every time that you have like a tube, a straw, a bottle or whatever, and then you can blow maybe on top of it, or just, you know, put some air into it, and eventually it's going to generate some sound. Okay, this is exactly the same case. So determine the frequencies of the first three harmonics of the covert if it is cylindrical in shape and open at both ends. So we are going to assume that this one is like both ends open tube. Okay, and the problem already gave you the numbers of the speed of sound, so we're going to use that one. All right, guys. They want the first three frequency, so it's going to be the first three harmonics. So this one is directly sort of like exactly what we just did there, right? So let me put it here, there, there. So we're going to fit first three, and because these are both ends open tube, so you're going to start from antinode to antinode. You just fit there, bam, bam, that's done. That's your first harmonic. Actually, you can just slide back and look at the slide. But I mean, we're just gonna practice by doing it ourselves here. So the second one, all right, you just do whatever you want. Just try to start with the antinode and then you ends with the antinode. You are good because we fit the boundary condition there. Same thing in the third case. You're gonna get, okay, I'll put one more twist to it. There you go. All right, that's it. Okay, so this is how it's done. It's pretty simple in terms of like, you know, just fit the wavelength into a tube. And now you just start counting, or you start analyzing the wavelength. For this one, you can see that it's exactly half the wavelength. So over here, you can say if the length of the tube is L, so half the wavelength is going to be L. And that means the wavelength is going to be 2L. And then the frequency is going to be V over 2L, and then just substitute the numbers, 330, 343 over twice the length of the tube, meter per second, meter here, and you are done.
Okay.
Okay, and it just show you one, right? But the rest, it will look exactly just like this. I mean, well, John, can I just like grab the formula and plug it in? The answer is yeah. Because once you understand this one, as I told you, like the end games of this one is so simple. It's like, okay, just having fun, fit wavelengths of the wave into a tube and just count them. Yeah. Nice. Okay, so I think that's how easy it is for you to try. The rest, I mean, you don't even have to do it. It's going to look exactly just like the previous slides. Okay, and the last exercise of this one is going to look exactly the same. Let's say if you are thinking of this tube to be, it's get blocked at one end. So that means what you have over here is going to be the condition that is one end open and the other ends closed. And if you want to start from scratch, you're going to have to start from antinode down to the node. The easiest case is going to be this one. And the next one, you just put one more twist to it. And then the next one, you put two twists to it. There you go. The conditions stay the same. All right, that's how it's done. And we don't need to do it, don't we? And you just say, okay, this one is the wavelength over 4 is the length of the tube. So the lambda is going to be 4 times the length. And the frequency is going to be V over lambda. And that is your fundamental frequency. Okay, and then on and on. And once again, if you slide back, yeah, it's going to fit exactly like this. Okay, but just to be able to identify the harmonic in this one, because as you see, as one open end, one closed end tube, the number of harmonics is going to be only the odd harmonics. So to be able to distinguish what kind of frequency that you're talking about in general, what they do is they put subscript onto the frequency. For example, over here, if you notice here, when you have fundamental, you put number 1 to it, right? And now you say about that, in this case, you said the first overtone is the third harmonic. The way that you can distinguish this easily, you just say you put the 3 down here. Does that make sense? So it's just helping you saying that, hey, the frequency of the first overtone is actually going to be 3 times. And then you can put this one as number 5 if you like. Okay, and this is going to be in contrast with this, because in the case of the both and open tube, the fundamental frequency, you can put number 1 in there. That's your fundamental all the time. But then as you can see, the first overtone is your second harmonic. You can put the second there. And then the second overtone is your third harmonic. So you can put the subscript 3 there as well. Okay.
Okay.
All right. So I hope that will allow you to understand all the terminologies, all the notation that they use. What does it mean by the subscript over here, and what it's trying to tell you about the system of the air columns and the standing waves inside that air columns. Any questions so far? Woohoo! All right. So if not, that's close down the topics on the material of this slide over here. But before we move on, I think I have to, I would love to mention this a little bit all the time. What kind of everyday like situation and stuff that you observe these standing waves in air columns? Any suggestion, guys? When that you're gonna hear this sort of like standing waves or the resonance or whatever the sound coming out of it? So the answer is this, guys. If you fill up a bottle of water with water, okay, so you fill up the water into a bottle, do you notice the sound coming out of it? It's gonna go like something like that, yeah. You hear this all the time, like, and then it's just like, you know, overflow or whatever. That's what it is. So the reason for hearing that sound, because I know, I'm supposed to do better at sort of like showing you some video or something like that. The reason is because when you start filling up the water, at first you don't have anything, right? So that means the sound that's going to come out of it will start from here. That's fundamental. Usually the fundamental will be the one that is the loudest, of course. But when you keep pouring in the water, yeah, the level of the water rises. So of course, now this is exactly the scenario of one open end, one closed end tubes. So that means, of course, your wavelength is going to get shorter and shorter and shorter as the level of the water increase while you filling up the bottle. And that's the reason why you start from a low pitch sound, because the wavelength is long at first. And once the level of water start creeping up, then the wavelength is going to get shorter and shorter, and then you hear a higher pitch sound at the end, and that's go something like that. All right. And this one is exactly that. You can play around with straw as well. I can grab a straw and then just blow. Okay, that's something that I can do. Okay. Yeah, here we go. All right, guys. So if you just grab a straw and then you just blow, you will hear some sound at some frequency out of it, right? Can you hear that? The reason that this frequency come out of it, because it's the length of the straw. Now everyone can guess, if I cut the straw in half, what will happen? So, and let's say I cut this in half. Okay. So you're supposed to hear a higher pitch. See that? But then it's kind of hard to tell. So the way that you can do is you just, if you cut the straw shorter and shorter, the frequency will just creep up in pitch. You can hear it. And then I cut it now. You know, it's a, you can cut it again. Oh, don't cut my own finger there. Oh, it's getting, okay. Now the pitch is so high. That's it. All right. You can play it at home. All right. But that's exactly the same phenomena that you observe when you fill up a bottle of water right there. Okay, guys, that's conclude this topic right here. Any questions so far? Alrighty. If not, then let's bring up the next topic. Okay. I mean, the next handout. And I think I put it here already. I'm confused because right now I was switching between the two tablets at some week and then not so sure which it is which. All right, guys. So the next one, oh, I think today we might be able to finish this class very quickly because I think we're moving along really well. So the next one that I'm going to introduce to you is the another kind of waves, which is the light wave. Okay. But as I said, I mean, every time we talk about waves, the knowledge about that sinusoidal functions and the stuff that you have already learned still works. Everything is great. However, the problem is this light, when you talk about light, it turns out it's the electromagnetic wave. So it's a wave that doesn't really have any medium. You don't have anything, you don't have like physical stuff for you to touch. Like there's no water, there's no string, there's no air molecule, there's nothing. It's just electric field and magnetic field that actually fluctuated up and down. So you can still call it's a transverse wave anyway. So it's a transverse. Oh, sorry. Okay. But it's because the direction of the electric and magnetic field is just perpendicular to the direction of the traveling waves. So that's fine. So that means if you have a light wave traveling, bam, so it turns out that will be the oscillation of the electric field perpendicular to it. That is the electric field. We will study those fields after this module here. And then perpendicular to that, you have the magnetic field that actually oscillating up and down as well. So that's why they both have the magnetic and electric in there. We name this electromagnetic waves. All right. But it's still sinusoidal, it's still sinusoidal function at the easiest setup of this electromagnetic wave anyway. So you're still good. All right. The knowledge of that one is still fine. However, we're not going to do that here. Oh.
Okay.
So the good thing about this one is we are not trying to study light under the topics that we already discussed, like superposition of light. You do interference of light. No, we are going to do something simpler than that. And I think you like this one. We're going to do something that we call geometric optics. Okay, every time that you try to study light using, like, you want to know what is happening to the light, where does it go, what happened to it, it's called optics. But every time that you try to study optics using purely just geometry, so that means you don't want to deal with, like, summation of sinusoidal wave, sinusoidal functions or all this stuff. We're gonna focus or contain ourselves within just the topic of geometric optics. So the good thing about this one is you only need geometry. Oh,
Okay.
isn't that cool? So that means there will be no like sine A plus sine B equal to 2 cosine sine. No, we don't have that. We're not going to have any integration, find the area under the curve. No, we're not going to have like differentiation to figure out the speed and acceleration. No, we're not going to have any interference. We don't have any combination of functions. No, we are going to use purely geometry to do the analysis here. Isn't that cool? So that will lift your whatever concerns or things are going to come that it turns out this topic is going to be super light to me. It's going to be like, oh, easy peasy. So that's kind of nice. All right. So we're going to contain, talking about only just the geometric optics. What are those? You're going to look at the reflection one more time, but the reflection will be, from the light as our sort of like a system to study. refraction. So this is going to be the highlight of today's lecture. And that will lead you to something that we call total internal reflection. All right. And next time, we're going to put some image formation there. How can you figure out the image from light beams or light traveling through optical devices on and on? Okay, cool. All right. So that's what we're trying to do today. So let's dive into it. Because we're going to use just geometry. So the fine detail of the waves, we can just let them go. Is that cool? So what I'm saying over here is this. So if you have light traveling from left to right, and you know you might be able to do it, you just like, oh, John, it's going to be, you know, some sinusoidal wave and stuff in there, right? Sine, cosine, kx minus omega t plus phi, blah, blah, blah. But say, hey, I don't care, because all I care about is just, we want to use geometry. So I just want to know where does the light is traveling, in what direction, where it's going to go, is it going to reflect, it's going to bend, it's going to, you know, flip flop, whatever. So you let go of that and you just only focus on the rays of light. What does it rays of light trying to do? Is just say, well, hey, it's traveling in the right direction over here. Just give it an arrow. And that's it. Well, it's not just a single arrow. It just means you have a path and then you put the direction to it. So that's why they name it a ray. So the easiest way to think of the ray is just a laser beam when you use in like your laser pointer and stuff like that. So when you see a beam of light, that is your light ray. That's good. All right. And then you can ignore those waveforms, wave fronts, or whatever disappear from your analysis right away. However, by focusing ourselves within just the topic of geometric optics, you have some limitation. Look at this one. If you have a wave coming in and now it hits an sort of like an opening, you have like an opening. So if you see over here, the wavelength is kind of like small in comparison to the opening. So as you can see, this is your wavelength over there and the opening is kind of huge. So if you can observe this one in other kinds of waves, for example, like water's wave, then you will see that the wave will just passing through the opening. It's just like nothing happens. With this one, you can still pretty much say that, Ajahn, I can still use the ray to determine the direction of motion of the wave. So far, so good. But once the opening gets closer, I mean, in space, so it means the opening gets smaller and smaller, you start to see wave spreading out after the opening. You have seen this, right? So you can notice this from maybe, you know, in the ocean or in the river and stuff like that, when you have a wave coming in and then you have some obstacle there, and then the wave is just spreading out and try to loop around or go around the obstacle or openings. So this one, we call this a diffraction. And now, by using the ray, it seems to have some problem here, because if the light hit the opening and it's going to spread out, what are you going to do with the arrows that you just draw over here? Yeah? It's just like, whoa, what to do? And if you keep squeezing down that opening, the diffraction effects will get even larger. So it means like, you know, the wave that coming out of it, it looks like a circular wave. So that's the limitation. Geometric optics will not allow you to do diffraction analysis. Is that cool? All right. So that's a good thing about this one, means we will not talk about interference anymore. And we will not talk about diffraction, which is another properties of light that can go around corners or obstacle and stuff. We are going to look at the main two properties of waves, which is reflection and refraction. And in this particular topics over here, we're going to use light to be our example of the waves that we're going to study. Even though any waves will do deflection, any wave will do refraction. Okay, but seems like light seems to be the easiest one that you can relate to. Okay, so that's why we, you know, all right, switch on the light and then see how it goes. So this is what's going to happen in our lecture here. So if you have light source, and the light source probably will generate light everywhere, right? So all you care about is just like, okay, where does the light go? Where does the light go? Where does the light go? Where? See, you can use the arrow or the rays to trace the path of the light. So for example, if you look at the path number 1, I don't know why when I undo it, it's jumping around. Sorry about that, guys. Okay, here we go. So if you look at the path number 1, for example, so you can see, but oh, Ajahn, I can trace this. It's starting out like this and it goes straight and it hits something and it's bent a little bit. That is fine. That bending of light, we call it the refraction. But as you can see, you only purely use geometry. Like you come in horizontal to the x-axis and then it bends a little bit with some particular angle, on and on. So you try to use geometry to help in to do the analysis here. Okay, so that's the stuff that we are going to do, and that I hope make you understand what kind of things that we are about to do here. Is the geometric optics right here. Cool. All right, that's done. So I think we're going to finish this slide and then we take a break. Sounds like a good one, because this is an easy one for you to grab. It's called the reflection, and you have a law of reflection that is very simple. You have seen this before in like a regular wave in one dimension. For example, we saw this in a wave on a string. When you send in a wave, hit the corner, it gets reflected. And if you remember, it's reflected like 180 degree backward, right? But that is the reflection already. But that one is simple because everything is in one dimension. The only way that you can go is either left or right. You just pick direction and that's that. But over here, because you have now a broader space, it's now two-dimensional. So if you look over here, if you have a light incident onto some surfaces, like over here, so at the point of contact over there, you will get a reflection of light. Is that cool? All right. And the law of reflection is very simple. It turns out if you make a measurement of the angle of incidence, so that means you take the ray and you make a measurement with respect to, now here we go, normal line. So every time that you have a point of contact over there, that's light is trying to do something. You draw a line normal to the surface of that. And in most formula, the angle that we talk about will be the angle that's measured with respect to this normal line. So that means if you have an incidence ray hitting this point over here, making, here we go, theta 1 angle, that angle means it's the angle with respect to normal line. Cool? All right, and same thing happens on the reflected ray. So on the reflected side, it will make another angle there as well. Okay, so still make a measurement with respect to normal line. So the law of reflection is simple. The incident angle must be equal to the reflected angle, and then you are done. Okay, it's simple. Everyone knows this one. However, just to make sure, when you have a law of reflection, the reflection must happen on a plane. You will never get reflection out of the plane. So that's why, I mean, just to make this law perfect, this ray over here, this reflected ray right there, and the normal light itself must be on the same plane. That is sort of like, you know, the property of this law of reflection. Okay. All right. So with that, then you can, you know, relate to something that you observe every day. If you have a surface that looks smooth, so that means law of reflection apply locally at every point. But because your surface is so smooth, it makes the reflection go out in pretty much the same way that it comes in. So in this case, you have a specular reflection, but it's nothing more than just a glossy surface. So the surface will look shiny. You can see yourself a little bit, you know, sort of like, you know, like a surface of a whiteboard or something like that. Yeah, smooth surface. But on the other hand, if your surface is rough, right, the law of reflection still apply locally. So that means at every single point of this one, the law of reflection has to apply. The incident angle equal to the reflected angle, and at every point you draw a normal line to it, so everything works. However, because now the outgoing ray or the reflected ray just sort of go all over the place, you're going to get a diffuse reflection. Okay, so it will not conserve the shape of the incoming beam anymore. The incoming beam sort of look very regular, uniform, but on the way out, it's get diffused. So this one is the same thing as the matte finish. So this one you will see it's like it doesn't have any shiny surface and anything, and it looks sort of like dull, and it doesn't give a good reflection off of it. Okay, so I think this is just a good sort of like relatable things that you can observe around you, and it's based on law of the reflection here. Okay, all right. A lot more fun will come after the break when we look at the refraction, and now we're gonna have then we're going to have some equation to apply. Sounds like a good plan? All right, so if this is good, then just take a break right here. I'll see you in 10. Yep. Okay, so what we have for you next is the refraction of light. And actually, it can be a refraction of any waves. However, light is kind of like easy for you to track. But you have already sort of like saw this kind of condition back in the topic of the standing waves a little bit. And if you notice,บอก sometimes อาจารย์ right, when you have the sound in the tube and there is the air outside the tube that waiting for the sound to come out, right? So if you compare the sound, I'm sorry, so compare the air inside the tube and outside the tube, actually they are different environments. So you can imagine that if the sound wave is trying to go from inside the tube to the outside the tube, that is the change of the medium somehow, right? Because the property of the medium are not exactly the same. Same thing over here in light. So you look at this scenario over here. If you have the interface between air and glass, and light try to penetrate through, I mean, it doesn't have to want to penetrate, but at least it's just light is trying to get from one medium to another medium. Like this one, it's trying to go from air to glass. So at the interface, that is where things start to happen here. So first thing first, there will be some reflection. You cannot avoid it. So every time light is trying to, or waves trying to change from one medium to the other medium, you will get some reflection in general, like this one. So law of reflection work. So you get a little bit of reflected ray. And you can say in general for air and glass, it could be somewhere around maybe like 5% reflection. So this is the reason why every time that you see, try to look through the glass window, you still see your own reflection a little bit off of the glass window. You cannot make it like you try to clean it, you try to polish it, you try to make it as transparent as you can, but no matter what, you can still see your own reflection a little bit all the time. And that's because there is a change in the medium of light that is trying to go from air to glass, glass to air, on and on. So every interface, there will be some reflection coming back to you. Does that make sense? Okay.
Okay.
Now, the main business of us is this. What about the part of light that actually get through the other side of the interface? So now the light is now going to get into the glass. It turns out, here we go. If you make a measurement of the angle, and once again, don't forget the angles are made, the measurement are made with respect to normal line. So the theta one will be your incident angle. Now it turns out if you try to trace the refracted ray, the outgoing ray that penetrate into the second medium over here, you get another angle there. So you can think of it as like the light is bent at the interface. It's changed the direction. Okay. And in this case, the direction is changing toward the normal line, which is fine. So the key is how can we determine these angles and what kind of law that govern this kind of, you know, the bending things or refraction of light? The answer is this. It's Snail's law. Okay. And this law is very simple, guys. It looks like this. It's like a product between two things are always fixed. Like this one is a product between the end that I will explain what this end is, and the sine of the angle that we just mentioned over there. So that's it. So what you have to do is just n of the first medium, sine of the incidence angle must be equal to n of the second medium and sine of the refracted angle. That is a Snail's law. Okay. Now here comes the question. What is that n there? It turns out we define the n to be the ratio between the speed of light in vacuum divided by the speed of light in that medium. And now, because everyone, I think, agree, and kind of like this is like a known fact already, that the speed of light in the vacuum, that's pretty much the highest speed attainable of any objects in this universe. So that means the numbers that you're going to come down here and divide this thing out is not going to be bigger than that, right? Okay. So that is a guarantee that the n that we define over here will have the value larger, or the best that it can do is just going to be equal to 1 in the case of the vacuum itself. Everyone with me so far? All right. So that means, all right, to figure out the n is just taking the speed of light, which has a fixed value around 10 times 3 times 10 to the 8 meter per second. And then you divide this by the speed of light in that medium. And because the light in that medium must go more slowly, like light travel in glass is going to move more slowly than in vacuum. It has to be. Light travel in maybe, water, light travel in maybe diamond, in silicon wafer, whatever, it's going to have a lower speed. So what you have over here is you're going to have that n for that material. This n has a name, and this name is the index of refraction, or refractive index. That's what it is. There you go. Okay.
Okay.
So why do we need this? I mean, why do we define this? Like sort of like, it looks like it's a reciprocal. It's like an inverse. N is inversely proportional to the speed of light in that medium. I think the reason for this is just because you don't want to deal with the inversion of the number all the time. That's my guess. All right. But the reason is because the speed of light is pretty much the highest in vacuum. So other numbers will get lower. And every time that you have to deal with something that's sort of like inversely proportional to each other all the time, then you have the division of that number. And here it's kind of annoying. So let's define n to be the inverse of that. So when we deal with n, you deal with the numbers that is larger than 1. So it seems to be easier to deal with. That's my guess. All right. Now, so maybe just a quick detour. Why light travel in other mediums more slowly than travel in vacuum? It turns out everything has to go back to the origin of the light itself. Because the light is the electromagnetic wave, and because the electric field and magnetic field are interrelated. So the change of the electric field generate magnetic field. The change of the magnetic field will generate electric field. And this process is just going back and forth and generate the motion of that light. Okay. And it turns out that sort of like these are back and forth between electric field, magnetic field will happen at sort of like the most efficient when there's nothing in the way. Does that make sense? So this means in the vacuum. So electric field will induce the magnetic field, and magnetic field induce the electric field back. When there's nothing in the space, that is the best for them to do the business. So when you put this light in some other medium, for example, let you put in glass. So you try to like, put this whole thing in glass, or maybe send it into a water. Now, inside that glass or inside that water, you will have like plenty of, molecule. You will have what? Electron, proton, nucleus, and all this stuff come in the between. All right. And because these are charged particle, all right. So don't worry, you will learn a lot more of this in the third module here. But anyway, everyone knows that charged particles will react to electric field and magnetic field. So these molecules, these particles sort of like come in the way and sort of like give this electric and magnetic field a harder time to induce each other. So that's why when it tries to penetrate through this material, it's getting more slowly, because you have to drive that electron along with me, and to send this one sort of like to induce the next one, like, all right, this nucleus come into the play. So there's so many things on the way, so that makes the process go more slowly. All right, so this is sort of like a rough picture, but it gives you a sense of what is happening in light travel in mediums other than vacuum. Does that make sense? So the reason I would like to explain this thing, because it's opposite to the physical waves. For example, sound, or maybe uh, wave on a string or whatever. So if you think about the sound waves, it needs air, right, to sort of like deliver that waves, right? So it turns out if the denser the air, the faster that you can send your wave through. Does that make sense? So it means sound waves can travel in a higher density material faster than the low density material because it has a sort of like when it's so dense, the mechanical stuff that's linked between them is going to be very tight. So everything that gets changed in one place will get sent off to the other place very quickly because of the high density of that material. So that's why if you send the sound in the air and then you compare to the sound in maybe like in ion, if you might have like, you know, like a big chunk of ion, and then you just, you know, just put some sound into it, you plug them, and then there's some bang sound, and then that sound will travel in the ion beam and all this stuff. It will travel much faster than in the air because the ion beam has a higher density and the sound can travel faster. So, okay, so I hope you see the opposite, the connections between the speed of waves and the density of the medium. So it's kind of opposite in light. Light doesn't need anybody else. It just need vacuum.
Okay.
Which means it just need nothing, pretty much. That's the best for them. All right, so that's concluded what the N is sort of like trying to tell you. The bigger the N means the slower the speed of light in that medium. Okay, so you can rearrange this Snail's law equation in another form if you like. You can put them in the ratio. For example, I can say, okay, Ajad, I can do sine theta 1 over sine theta 2. And then you just move the N around. So it's going to be equal to the N2 over N1, no problem. And now because we know the definition of the N is just inversely proportional to the speed of light in that medium. So N2 over N1 will be equal to V1 over V2. So far, so good. Nothing is done. And then you can apply one more step to it because everyone knows V equal to F lambda. So that means I can chain this one through the ratio between the wavelength lambda 1 over lambda 2. So far, so good. But then here comes the question, but Ajahn, why don't you put F1 over F2 into it as well? When everyone is already there. The answer is, this is the dude that has to be fixed. Something has to be a constant. I mean, constant in this case doesn't mean the constant of the universe or anything, but it means it's an actual movement of something, right? It's the wave. Even though electromagnetic wave, it's something you might not be able to grab on it, but there's an electric field, there is a magnetic field, so there must be the source that's generating it. So what I'm saying over here is this, guys. The reason that frequency has to be the same all across the interface and all the material. Think about it. If I send in waves, and let's say this wave is 1 hertz, simple as that. So it means every 1 second you move the whole thing 1 complete cycle. This is real. This is reality. You cannot change this one. So it means in 1 second, let's say if it's a wave on a string, you have to move your hands up and down and up back to the original position. That's real. That cannot be changed. That is the fact. So that means if you have 1 hertz wave generated, it means the something must have already traveled 1 complete cycle in 1 second. No matter where this one go, if it's already gone through to the other medium, you must get exactly 1 cycle in 1 second. Does that make sense?
Okay.
That cannot be changed. So that's why the frequency is the one that is going to like have the same value all across the movements of this wave, no matter which medium this guy trying to get into. Okay. And this is a good thing because with that MF fixed, so when you look at this one, so the things that is going to change in that medium is going to be just the wavelength. Because once the velocity is changing, which is okay, n is but larger than 1, things get more slowly, then that means the wavelength is going to get extended. It's going to get a little bit bigger, but that's fine. The frequency stays the same. And this is the reason why you can still see light at the same color with your eyes. Does that make sense?
Okay.
So think about it. If everything just keeps changing when you change the medium, And then think about it. If you try to look at the red light in the air, and now you dive into the water and then you look up again, then that red light might turn into some other colors because the frequency gets shifted, and that doesn't make sense, right?
No.
So that's why the only thing that is going to get exactly the same, it won't change, is the frequency. So the frequency from the LED lights get to your eyes, and then your rod cell, cone cells, whatever the cells in your retina, still get that frequency and react to it as a red, and it send the signal to the brain and they say, okay, that's red light. So, all right, and maybe I speak too much already. But that's what it is. All right. So the frequency is the one that gonna get exactly the same, won't change across the whole movement of that wave, because it's get generated like that. It's simple harmonic motion, for example, right? You know, it's actual movement of the source that generate the disturbance that cannot be changed. Okay, guys, let's give it a shot and see how the refractions through Snell's law can be applied. But before get to that, I think there is like a big sort of picture that you will agree with me that it won't get out of these two cases. There are only two cases will happen in the Snell's law. Look at this one, guy. So if you send a light beam from air and then it tries to get to the glass, so end of the glass will be given, end of the air will be given. Oh, I put it, there you go. That will be end of the air and end of the glass. And because air is pretty like, you know, light and not a lot of stuff. So there's a table down here that's showing you what should be the value of those ends of the materials there. The vacuum end is exactly 1. Now, end of the air is, as you can see, it's like, well, end and a little bit. So you can approximate all the time that the end of air is, let's say, is 1. Now look at the glass. It could be just a regular glass over here. N is 1.5. So that will allow you to see, yeah, speed of light drops by how much? By knowing the value of the N. But then from Snell's law, when the light's trying to go from air to glass, so you're coming from a smaller N to a larger N. By Snell's law, it's the product between N and the sine theta. So that means you are going from theta 1, and then you must go to a smaller theta angle. You guys with me? Because you're coming from small n to a larger n, the angle must going from larger angle to a smaller angle there. So in this case, you're going to get the refraction that bend the light toward the normal line after the refraction. The opposite case, which is the only other case that's going to possible, is if you go backward. If the light try to go from glass to air, the glass has a bigger end than the air, so the angle will go from a small angle to a larger one. So in this case, the refraction will happen to bend the light away from the normal line. That's it. These are the only two cases. What else can it be? And the rest, you just figure out those two angles through Snell's law. All right. And then you can refer back to this table to look at the value of those ends. Sounds cool? All right, that's easy enough. Let's give it a shot and see how it goes. A ray of light strikes a flat block of glass given n equal to 1.5. The thickness is given to be 2 centimeters. All right, so you have a block of glass at an angle of 30 degrees with the normal. All right, that's cool. So they already give you that information there that the light hit this surface at 30-degree angle with normal. Trace the light beam through the glass and find the angles of incidence and refractions at each surface. All right, cool. So what you have over here is every time that you try to apply Snell's law, you apply at a point. Don't think too much. Whenever you look at a point, then that's it. You do analysis at that point, okay? So what you have over here is definitely, for sure, you will get some reflection, which we don't care much, okay? That's just a partial reflection, that's fine. Now, there will be some penetration to the next medium. And now let me highlight this one, that is the end of the air, which always, set it to 1. And in glass, let me put just the subscript G for that is 1.5. So you can imagine that you're going from 1 to 1.5 in the value of n. So you go from small to larger. The angle will go from big to smaller. So you can see that now the bending will go something like this. Does that make sense? Okay, so the refraction will pretty much give you the bending light towards the normal. All right, and I can call this point A. So you can say at A, N A sine 30. You guys with me? I'm applying Snail's law right away. Equal to, now move on to the second medium, which is glass. So it's going to be N glass sine theta. And let me call this angle theta right there. And that's it, guys. N air is 1, sine 30 is 1/2, N of glass given to be 1.5. And from here, you can figure out what should be the theta. You're done. Cool. That's how easy it is to apply Snail's law. Now look at the bottom interface. You still have one more interface to look at down here. So once again, when you have this, every time you draw a normal line right there. Okay, and if you zoom in, if you already saw that the refracted angle right there is theta, definitely here, this is going to be theta as well. Same angle right there. This is also theta. So that means, let me name this in the point of contact over here is point B. So at B, now you try to figure out what happened after this interface. From the look of it, because you come back into the air, in air is 1 again. So at point B, you have the case of coming from larger n to a smaller n. So you must pretty much go from smaller theta to a larger angle, right? So over here at B, you're going to have n glass starting from the upper portion of the interface, sine theta, we already figured that out, equal to, now you come out into the air, so it's going to be n air, and then sine what? But from the look of it, wait a second. You see that n glass sine theta, it's already here, n glass sine theta, right? See that? So, well, Ajahn, it look exactly the same. Well, yeah. So that's the reason why you know exactly that this light gonna come out 30-degree again. No change. Okay, it just come out. And that's it. So you don't even have to calculate anything pretty much. So it's gonna come out 30. And that's it. It's done. Cool.
Okay.
Any questions? So it's very easy to apply Snell's law. Just, look at the point of refraction and you just apply Snell's law right away. That will do it. Okay, but in reality, don't forget, there are some reflection anyway, right? It won't, it won't disappear. So let me put like a faint reflection or somewhere here. There's a reflection there. This will give you reflection as well. And it's going to refract out, believe it or not. And that portion right there will get partially reflected down here and get refracted seriously. Right? But it's getting thinner and thinner in intensity. Right? There will be multiple reflections and refraction going on. All right, but we mainly going to look at just the main big one because we know those partial reflection is only like 3%. So after a couple of multiple reflection, it's pretty much like die away. We can just ignore those. Okay, cool, guys. This is what's happening with the Snell's law. All right, now try again, guys. Try this one. When the rectangular metal tank in the figure is filled to the top with unknown liquid, the observer or with eyes level with the top of the tank can just see the corner. So your eyes doesn't care where does the light actually comes from. Once it hit the eyes, then your brain will interpret that it's just in front of you. So over here, the image of the corner of the tanks gets get refracted at the surface of the water or of the liquid over here, and it just bend 90-degree, hits your eyes. That's just level with this surface right there. Cool. So it doesn't matter, right? So your eyes will see the corner of the tank anyway. So if the D and the L, the dimension of the containers, are given, so what is the index of the index of refraction of the liquid here? Okay, so how do you do this one? Well, Ajahn, no problem. Look at the point of refraction is right here. I put like a black dot right there. So you see that it's going to make the angle with normal. Don't forget the normal line here. It's just right there. So let's say the incoming angle, let me just call it the theta. But now the refracted ray is so easy to see that it's making 90-degree angle on the way out. Got that one? Yeah, so far so good. So let me name this point P. So let's say at P, you can see that now starting from the bottom, from the liquid. So it's going to be end of the liquid, sine theta, that's done. Now move up to the surface in the air. So it's going to be end of the air and now sine 90 degree. That's it.
Okay.
So far so good. All right. Now in air is 1, sine 90 is also 1. Now the sine theta itself, that's not so hard to imagine because over here is just the opposite over hypotenuse there. And the hypotenuse over here is just going to be d squared plus L squared. So over here, I can answer you there. NL is going to be 1 over sine theta. And the sine theta is just the opposite over hypotenuse there. I just move hypotenuse up top and then the opposite is down here and you are done.
Okay.
Cool. That's very easy. And the good thing that you can check, this is like a sort of like good point to check your final result. This number is larger than 1 as expected because we pretty much agree that n couldn't be 1 because this liquid is not supposed to be a vacuum. So the only choice that it's going to happen is n must be larger than 1. And the rest, just plug in the numbers and you're done. So far, so good. All right. Now, what is so interesting about this sort of like refraction business over here is the next one, guys. Okay. Oh, not this one. This is just an example. All right. Sorry. I thought we're done with the example. Sorry. My bad. Oh, okay. Sorry. Okay. So we have another one, but this one is once again is easy to try. So once again, look at the point of refraction. Let me name this point P. Now everyone should be comfortable doing this one right now. So let's go quickly. I think this is why at point P, because the information is solid here. So it's kind of like point O. Yeah. So at P, what happens? Well, Ajan, that's easy. N air, start from the top. Sine theta, that's fine, equal to N oil. And now what is the angle over here? If you look at this one, Ajan, oh, it's 20 is already given there. So that means this angle must be 20 as well. Perfect. Just plug it in there, sine 20. All right. So that's how you determine the theta. And it's already done. Sine theta is going to be in oil is given to be 1.5. Sine 20, punch the calculator a little bit. In air, you set it to 1. So over here, you should be able to figure out theta. Done.
Okay.
Cool. At O, no problem. All right. So let me put a green dot right there. You do exactly the same thing. Starting from the top portion, that's fine. In oil, side 20, right here. That's the angle of incidence there. Must be equal to on the way down. Now it's water. That is okay. It doesn't matter. It's in water. Let me put W there. And then you put the sine theta prime in it. And that's it. You're done. Okay. And as you notice, one more thing, the in oil side 20 is exactly here. So that means whatever you're trying to figure out down here is going to be exactly the same as here as well. So they are all the same. That's pretty much the structure of Snail's law. The product between n and the sine of the angle of incidence always the same across the whole thing, right? Because the geometry here is easy. So it's just like, n times sine theta stay fixed throughout this refraction, okay? Even though you have multiple materials now. All right, guys, cool?
Okay.
All right, so now it's easy to use. So what is so cool about this one? And I think this kind of question just pop up. If it's pop up in the exam, that will be too easy for you. So what's more interesting is this, guys. This is a scenario that's worth discussing. Now, in this scenario, the light is trying to go from bigger n into a smaller n, like this one. Want to go from glass all the way to air. And everyone knows the refraction will make the bending away from the normal, right? After the refraction. You guys with me? So think about it. if you start by hitting this light perpendicular to the interface, so your incident angle is 0, so nothing happened, it just go through, right? So Snail's law is like 0 equal to 0, nothing is going on. But then you keep increasing your incident angle right there, so your refracted angle will get larger. This one is fine. See, all right? So it's getting bigger. Now, what happens if you keep increasing your incident angle? Of course, Ajahn, your outgoing angle will be bigger as well because it's bent away from the normal, right, guys? So I keep increasing the incident angle. So I will get even larger outgoing refracted angle. Now, there must be a point where your incident angle give you a 90-degree outgoing refracted beam. Whoa. Wow. What will happen then? That's a problem. The problem is, after this angle, you will not get any refraction anymore because the Snell's law seems to not applicable anymore, and you won't get anything out of it. So that's why we say this particular condition over here lead you to the critical case. Is the case that you won't get refraction anymore after this angle. So that's why we name this angle the critical angle. This is critical. Okay. And after this, you will only get perfect reflection. So we call this phenomena total internal reflection. It's total, so it means there will be no more penetration into the second medium, so there will be no refraction happens. And the angle that determines the starting point of total internal reflection here is called critical angle. How can you figure out critical angle? Very easy, still Snell's law anyway. So look at this case. What do you get? Well, Ajahn, start from it. It's going to be n glass. So let me write on top over here. N glass sine theta critical is going to be in air in this case. And then sine 90 degree. You guys with me?
Okay.
That's all you care about. Just set 90 degree into your refracted angle. So that's what it is. So the conclusion is you can figure out critical angle by setting the N1 side of the critical angle that you want to pick, you want to calculate. And then you set it to N2, the second medium, and then you set angle of the second medium, refracted angle to be 90 degree. Sine 90 is always 1. So the sine of the critical angle is just going to be ratio between N2 over N1. And because N2 must have the value less than N1, because this condition only happens when you try to move the light from bigger N to a lower N. Yeah. So that's why this ratio will never go beyond 1, which is perfect. That's the value of the sine theta. Sine theta never go beyond 1 anyway. Cool. That is conclusion. Where have you seen this kind of total internal reflection in real life? I don't know, have you seen this before? But when you dive inside a pool and stuff, and then you like try to look up back into whatever the sky and things, sometimes you don't see the sky, but you only see the reflection of the bottom of the pool. Have you seen this before? So this figure showcases that your surface of the water air interface acts like a mirror instead of, it's not see-through interface anymore. Cool. That means you are looking right. Not, it doesn't have to be right exactly, but the condition that you are at, and then the angle of the eye that you are trying to look up into the sky fits the total internal reflection condition. So you won't see anything beyond that. It's going to be the reflection instead. Cool. All right. And where else have you seen this kind of, you probably might not see it anymore, but where else that you are using this total internal reflection? The answer is your broadband internet, that fiber optic stuff in your house. So they use the optical fiber to send the data signal through the, using the light instead of electrical signal through the electrical wire. Okay. And to be able to send light through a optical fiber, then you have to use this total internal reflection here. That's what it is. All right. So the figure on the left is exaggerated. So the light doesn't really like go bow, bow, bow. No, it's not like that, right? It's more like it's try to start like light that follow the total internal reflection condition will just pretty much like, I think it's more like curvy stuff in there. It's sort of like curved back and forth. Yeah, because the way that they engineer the optical fiber is not like a single value of n. So it's more complicated in real world. But the concepts that being used here is just the total internal reflection. Okay. All right. And then you probably have seen some toys or some decorative items that look like this. It's like a plastic, it's like transparent plastic or polymer or whatever fiber. All right. And then there's a light source underneath. And then that light just travel through that tube and ends up at the tip of the cable. And it looks like nice and cool like this. Yeah. So that's optical fiber in real life right there. But I think that's just cheap plastic though. That I don't think that's one that being used in like internet optical fiber. Yeah. Okay. But anyway, anything works. All right. You can even do this total internal reflection using water in your house. Yeah, and then there'll be some experiments that you can do at home. So if you do the YouTube search, do like total internal reflection experiment at home, then there'll be tons of stuff that you can play around with the laser pointer and some stuff in your house. Yeah, that will be a lot of fun there. Okay, guys. So come back to our business over here. I think the last thing that I want to sort of like discuss today is this. So once you know how to calculate the critical angle, so every time you have to make sure that the critical angle comes in a pair of material, right? Because you have to pair the two. Like this one is going to be critical angle between air and glass pair. So you usually, and not usually, you cannot talk about critical angle of some material. It doesn't make sense. It has to be one material against the other material. So the other example that you probably will be able to relate to is this exercise right here. Let's say calculate the critical angle for the following material surrounded by air. So you pair with the air. So that means I can do this. Diamond air critical angle. How can you calculate that? No problem. So you say, okay, if you don't want to memorize the formula, you can do N diamond. Okay. Side of the theta critical, the light try to come out from the diamond into the air. So it's going to be in air, and then you put sine 90 to it. Does that make sense? All right. But if you do the exercises for a couple of times, you probably can memorize the formula. You can just say the sine of the critical angle is just going to be N2 over N1. And that will be 1 over N of the diamond. If you go back, look at the table over here. But whoa, diamond is like huge value of N. And that makes sense because diamond is so dense. It's one of the highest density material in, not in the universe, but at least in on Earth, I guess. All right. So what it is, that seems to make sense because light will have a very hard time trying to penetrate through diamond. So that's why it moves really slowly in diamond. So N is huge. So let's take like 2.4 into it. There you go. All right. And then you can calculate theta critical out of this one. If I remember correctly, I think it's about 24, not degrees Celsius, sorry, 24 degree. Okay, approximately. All right, you can check my numbers again. But then you can do this and then compare this to glass air critical angle. So you do N glass sine theta critical. And on the right side will look exactly the same. N air sine 90, which is 1. So sine theta critical for the glass air pair is going to be N air over N glass. And that's 1 over, once again, refer back to our table here. You can take 1.5, let's say, for the glass. So N of glass is about 1.5. There you go. So if I remember correctly, this one is approximately, let's say, about 32 degrees. What can you conclude out of this? Do you notice something here? Right, and that's the purpose of this exercise right here. The diamond air takes only 24 degrees for you to hit the total internal reflection. But for the glass air pair, it's take up to 42 degrees before you can see the total internal reflection. And this is the reason why the diamond is so sparkling. Does that make sense?
Okay.
Because it's just so easy for you to hit the total internal reflection. So that's mean the light that get into the diamond has more chance for it to reflect back out because the critical angle is small. Plus, you add like diamond cuts on top of it, right? There's so many angle of light that can just go in there and then get reflected and eventually will just come out back to you. So when the light so easily get back to you, that's your sparkling stuff, bling bling and all this stuff right there. Okay, so that means if you take the glass and do the diamond cut to the glass, it won't be as shiny as diamond. This is the reason behind it. All right. Plus, if you use other material that might not be as good as diamond, but the N is higher than glass, you should have a better chance for get some bling bling sparkling stuff. And that's what it is in like maybe Swarovski, sapphire, and other stuff. As you can see, if I can pinpoint that here, sapphire is somewhere, is larger than glass, of course, but it's not going to be as high as diamond, but at least it will give you a better property in terms of make things a little bit more sparkling, to your eyes. And that concludes today's lecture, guys. You are done here. Any questions so far? All right. If not, all right, guys, take care. And then I will see you guys next week. Okay. And if I have a chance, I'll try to grade your first exam. Okay. I'll keep you posted. Yeah. All right, guys. Stay safe, and I'll see you guys next week. All right. I will post homework during the weekend. Yeah. Okay. Bye-bye, guys. Take care.